All righty. Hello, everyone. Can you hear me okay? A thumbs up is good enough to know. Oh, all right. Awesome. Awesome. Well, firstly, I would like to welcome everybody here to the 2024 Undergraduate Showcase for Black Space Week, hosted by Black and Astro. I am Robert Washington, the COO for Black and Astro, and I'll be moderating this event that we have here. Let's see. So first, I would like to start with a brief introduction of our judges here today with us for the panel. So let's see. First up, we have Michael McPherson. He is a Atlanta, Georgia native who studied aerospace engineering at Embry-Riddle Aeronautical University. He recently received his master's in atmospheric science from Howard University and will be continuing his education at Purdue University in their atmospheric science PhD program. He has worked on various missions within NASA as a contractor and researcher, the most notable being his experience as a quality engineering intern and fluids engineering intern for the Artemis 1 mission and International Space Station processing facility at Kennedy Space Center. Contributions to the ASMLS airborne mission, as well as NASA JPL, and his current work being conducted on the Tigris mission at Goddard Space Flight Center. Michael is versed in thermal engineering analysis, orbital mechanics, and economics, and is excited to see the intersections of space and environment through research and operations. Let's see, is Michael here? Awesome. Great. Next, we have Tinley Hutchinson Smith. She is currently researching on theory, which includes modeling Thorne Zyko objects and other systems throughout the universe that contain black holes, big and small. Their PhD advisor is Enrico Ramirez Ruiz, and their past undergraduate research includes the study of barred galaxies using Galaxy Zoo and Hubble Space Telescope data, the extent of active galaxy nuclei in the Illustris simulation, and the study of X-ray binary light curve variabilities using CXO data. All right. And last but not least, we have Naya Butler Craig, who is also part of Black in Astro as well. Um, they're a native from Orlando and are working towards her PhD in aerospace engineering and is a NASA Space Technology Grant Research Fellow and Jim Fellow at the Georgia Institute of Technology. Her research involves characterizing the electron energy distribution function at the inner front pole cover of a magnetically shielded Hall effect thruster and a centrally mounted cathode using laser Thomson scattering. Welcome, Naya. So for those who don't know or would like a refresher, today's undergraduate showcase is an opportunity to hear from a handful of undergraduate students about their current research and their research achievements. Each student will be presenting a 5 to 7 minute lightning talk on their research, and that will be followed up by Q&A from judges as well as sorry, as well as other people we have in our audiences here today. Let's see. So to start, we will have Jasmine Freeman from Valdosta State University.
Thank you for the introduction. Do I go ahead and start?
Yes, please.
And do you need me to share my screen, correct?
Yes.
Perfect. Can everyone see?
Yes, we can see.
Everyone can see, right? Like my screen sharing, right?
It appears black.
Okay.
I only see a black screen. Oh, I can
How's
see.
it?
Yep,
I
there
can
you go.
see.
Awesome. Perfect. So I am excited to present my research. The primary goal of our research project is to determine the elemental composition of 6 chosen stars. These stars were selected to represent a broad range of temperatures, ensuring that we observe a variety of distinctive spectra and spectral classes. By dissecting their continuous spectra, we aim to uncover some of the secrets hidden in these stars. So, of course, to achieve our goal, we employed some equipment like a CCD camera for capturing high quality images, a 6-inch celestron telescope that provides the magnification that's needed to observe these stars, and then some color filters. And that's to help isolate the different wavelengths of light for more detailed analysis. So, as we progress, the next stage of our project involves integrating a spectrometer or spectroscope. However, at our school, we do not have those sort of necessities, so University of Michigan offered us an atlas so that we can compare the continuous spectrums with their absorption spectrums. When we dissect the spectra, we focus on identifying absorption lines, which is those dark gaps in the spectrum. These lines are crucial indicators of the elements that's present in the stars. For instance, hydrogen and helium are typically excited in stellar atmospheres, and that creates distinct absorption lines. And in some stars, we expect to see remnants of metallic lines, which can provide further insight into their composition. So here are the stars here, our beautiful, beautiful continuous spectra. And it's essential to understand that metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. And this property can help astronomers gauge these stars or nebulous formation period. Low metallicity suggests an older origin, and basically is when it's formed when the universe had fewer heavy elements. And then higher metallicity indicates a more recent formation, reflecting enrichment from previous generations of stars. And so the strength of Balmer lines, which are specific absorption lines of hydrogen, is related to a star's temperature and stage of evolution, but does not necessarily increase with age or decrease in temperature. Now, once we got past the atlas part, we go into the results of each of the stars that we chosen, and we see that for one, Bellatrix, it appeared blue and white, and the spectrum had neutral helium lines and strong hydrogen lines. Vega appeared white with a bluish shadow. It's a very, very hot star. And the spectrum, it has very strong hydrogen lines with weak ionized calcium lines and weak ionized metal lines. Polaris, our North Star, it appeared yellowish white, and it had very strong hydrogen lines, strong ionized calcium lines, but it had weak sodium lines and many ionized metal lines. That's interesting. Capella, the appearance was yellowish orange, and it was like a giant, so it was a very big star. And the spectrum had neutral metallic lines and ionized calcium. Aldebaran, appearance was an orange giant, so it's also a very big star. And the spectrum is very weak hydrogen lines with strong ionized calcium lines, with strong sodium lines, and many, many lines of neutral metals. And last but not least, Betelgeuse. I won't say it 3 times. The appearance was very red. It's also a pretty big star, and the spectrum has metallic lines such as iron and ionized calcium. So calculating the elements of stars is not just an academic exercise. It helps us determine several key characteristics of stars. and that's stellar density, help us to understand temperature, as well as the stellar makeup of each of the stars. In summary, our research project aims to unveil the secrets of the stars by analyzing their spectra. Spectroscopy is a powerful tool in science, enabling us to determine the composition, temperature, density, and motion of celestial objects. It is instrumental in advancing our understanding of the universe. By using specialized equipment and advanced techniques, we strive to contribute valuable knowledge to the field of astrophysics. Our findings will not only enhance our understanding of stellar composition, but also pave the way for future discoveries in the vast expanse of the universe. And I would like to give a thanks to University of Michigan if anybody is from there. Thank you.
Thank you.
Thank
Applause.
you.
And now we can see if there are any questions from, I'll start with any questions from our judges, and then I'll move into the Q&A from our attendees. All righty.
Thank you so much
So
for the
we have
great.
one question in the Q&A. And this is from Flor Brocardin, and my apologies if I am mispronouncing your last name. Great presentation, Jasmine.
Thank
They
you.
were curious, yes, they were curious, how long did you have to observe each star before you achieved the spectra?
Oh, that's a great question. So this project took place in November, hence it was very cold. And so if we stayed out there for too long, the telescope will start to freeze. Very funny. So it took approximately 5 months for all the stars. But I will say that, for instance, Vega, which is the hottest star that we observed in the chosen selection, it took a little bit longer. It was very bright and it was very cold outside. And so it was very hard to get that one because of its luminosity. Does that answer your question?
I believe so. There haven't been any updates in the messages. Any other questions for Jasmine? All righty, so we will move to our next presenter, Mariah Jones from Vassar College. Mariah is a rising senior at Vassar College and on track to earn her Bachelor's of Science in Physics and Astronomy with a concentration in French in May 2025. She is actively engaged in two research groups, one focused on simulating hydrodynamically turbulent material in the circumgalactic medium under the guidance of her major advisor, and another studying the polarity of Sagittarius A with her South Pole Telescope research team. Maria's passion for astrophysics began early. She joined her first research group as a high school senior, working with Professor Brett Andrews at the University of Pittsburgh. Her research experience has since expanded through several notable projects. In the summer of 2023, she interned at the University of Chicago in collaboration with SBT, working on a project focused on modeling asteroids and using microwave telescope data to constrain their thermophysical properties. In the summer of 2024, she will be at the SETI Institute investigating the impact of a planet's residence and a crowded non-resident system on the stability of potential co-orbital companions. Known for ambition and high motivation, Mariah is deeply committed to her work, She brings optimism and positive attitudes to every endeavor, aiming to uplift her coworkers, peers, and mentors. And without further ado, Mariah Jones.
Thank you so much for that introduction. I'm really excited to share my previous summer research project. Let's see if we can. Okay, is everyone seeing my screen good? Okay, perfect, awesome. Yes, so I'm really excited to talk to you guys about modeling asteroids and how I was able to use this model to constrain their thermophysical properties. So before I get into the science of everything, I want to give a little background on what the South Pole Telescope is, where it's located, what it does. Basically, it is an actual telescope located at the South Pole Telescope due to its ideal environment. It is very high in elevation, and the climate is very low in humidity. So the atmosphere is very low, and that helps decrease the interference with the scans. And basically what it does is it measures the cosmic microwave background, which is just the light left over from the early universe. And so it stares at a patch of sky for an extended period of time, and it will just read through that patch of sky back and forth, taking small images and compiling those images together. And these are very long exposures. Now, you might be wondering how the cosmic microwave background has anything to do with asteroids, and I'm here to tell you that it, in fact, does not at all. They had a bunch of interesting data and images of transients that would pass through the scans while they were looking at the cosmic microwave background. And with this information and this data, they decided to birth a project, and herein lies my research project. So essentially, we wanted to determine whether or not the South Pole Telescope data would be useful in constraining the thermophysical property known as thermal inertia. And basically, the thermal inertia tells us a lot about how temperature is distributed with respect into the asteroid. And basically, it tells a lot about the thermal conductivity, the density, and the specific heat capacity of a specific, in my case, asteroid. And this is important because this can tell us a lot about the composition of asteroids and thus how they formed. And you can take this into a lot larger scales, such as how the universe formed, which is a lot more aligned with the South Pole Telescope and their image. But so my project was zeroed in on asteroids, and the first part of it was to create a Python interface capable of realistically modeling an asteroid. And so I have this image here. What I wanted to do and what I was able to do was load in an asteroid shape model from an online database, rotate that asteroid shape model so you can see this asteroid rotating. And basically, as you go deeper into the asteroid, we focus on a specific facet, which is just an area on the asteroid. And we want to update the temperatures as you go deeper into the asteroid. So I have this image here of basically the surface temperature, and then you go, I believe, 4 centimeters deep into the asteroid surface, and you can just see the temperature gradient as you go deeper in. It starts off pretty red, correlating to the subsolar facet and the sub-Earth facet. So, and then as you go deeper into the asteroid, the gradient sort of shifts. And ideally, if this image were to go on for an indefinite amount of time, the entire sort of interface and the facets that are visible are the facets that would be visible from Earth. Ideally, if this were to go on for an extended period of time, each of the facets would have this sort of white neutral color to represent thermal equilibrium. And so that was the first part of my project. And the second part of my project was to compare our outputs of the simulation to actual data. And we wanted to do this for 2 reasons. Firstly, to check the accuracy of my interface, and secondly, to constrain the thermal inertia. And so we decided to pick 3 alternate microwave telescopes in addition to the South Pole Telescope. And we can see this plot here. So what I have on the y-axis is the ratio of measured to modeled flux outputs. And on the y-axis, I have the wavelength. And I have this reference line at y=1 because we want the measured and the model to be the same. So we want the points to sort of we want the points to converge to this y=1 reference point. And we set the thermal inertia value equal to two different values. So one rather small value and one relatively high value. And you can see when looking at these two graphs on this, looking at the y=1 reference line, where the thermal inertia value is equal to 5 versus where it's equal to 80, the points have a closer correlation to the reference line of y=1. And what that tells us basically is that this specific asteroid that I was modeling, which is Pallas, more than likely has a higher thermal inertial value, which tells us that the thermal conductivity, the density, and the specific heat capacity are all on the higher end of things. And with with these two images, it's also important to note the error bars. So these pink dots here are flux measurements from the South Pole telescope, and these others are from the other telescopes. And it's important to note that SPT seems to almost have no error bars, which of course isn't the case. It's just the fact that the points are extremely accurate due to the long exposure the telescope has on the asteroids. And that's something that the other telescopes don't have. And so in conclusion, I was able to deduct that the South Pole telescope has an extreme impact and would be extremely useful in constraining the thermophysical property known as thermal inertia and other thermophysical properties due to the high precision and very high reliability of the data points. And of course, this is due to the unique detection method of the telescope, allowing for long exposure of the asteroids and highly accurate flux measurements. This project was extremely successful. I was able to yield results within, I believe, a factor of 0.2, so 20% in just a short amount of 10 weeks. And so just thinking about what I would have been able to do had this project continued. And there's actually more work being done at University of Chicago, South Pole Telescope, and UIUC. So yeah, this was overall a very successful project, and I'm very grateful to all of my peers, my mentors, and specifically Paul Tuchura, who was my grad student, and Tom Crawford, who was my PI. This was an amazing experience, and I thank them sincerely. Thank you guys so much for listening.
Awesome. Great job.
Thank you.
Any questions from our judges or audience?
Yes, Michael.
Yes. So I had a quick question about taking the thermal inertia data that you have. This
Yeah.
might be, you know, something beyond what you've already looked at.
Mhm.
But were you able to determine like specific elements that asteroids were comprised of based on the thermal inertia data? Or was it you were just testing the feasibility of the South Pole telescope?
Yeah, that's a really awesome question. Thank you for that. So okay. There are a lot of different thermophysical properties, and basically they can tell you a lot of different things about the composition of the asteroid. And the unfortunate part about the thermal inertia is that we can't actually measure that from observations. So what we are able to measure though is the flux. And so what we did was I wrote a function able to calculate the flux based on the temperatures of the facets. And with this flux, we were able to derive, well, we didn't derive it. We were able to utilize an equation and sort of parameterize the thermal inertia and set the different values for the thermal inertia. And so taking the flux, we were able to get to the thermal inertia. So we weren't really able to observe that directly. And we weren't really able to optimize our interface because we unfortunately were on some pretty tight time restraints. But we were only able to deduct that because Pallas specifically has a higher thermal inertia, more than likely has a higher thermal inertia value. We can infer about the properties of the composition, but we didn't necessarily or explicitly determine what the different properties or what the different composition materials would be, if that makes sense. So one of the next steps we were looking at, or we would have been inclined to do had this project continued, was to account for more complex scenarios. So accounting for different surface materials and craters and things like that, to be able to sort of get a more finer view of what the asteroid is actually composed of. Does that answer your question at all?
Yes, thank you.
Perfect. Of course, of course. Jasmine?
Hi, Mariah. Your presentation was amazing.
Thank you so
So I
much.
had a question about
Yeah.
like the subsurface composition. I
Mhm.
was wondering, how can we differentiate between surface and subsurface compositions of asteroids using
Mhm.
microwave data?
Yeah. So I actually really like that you pointed this out because I forgot to mention this. So the reason why the South Pole Telescope is the reason why this data is so important into the scientific community of this within this field is because most asteroids are observed in the optical and the thermal or infrared wavelength regimes. And if you want to learn more about the composition of an asteroid, you want to see deeper into the asteroid. And so microwave on the electromagnetic spectrum, they have longer wavelengths, so you're able to reach deeper into the asteroid and see a lot more. Reaching deeper into the asteroid, you're able to, see more about the inner workings of the asteroid. And so microwave telescopes specifically are able to, reach that deeper. And radio telescopes would even be more incredible, but that's a whole different thing. But you're able to see deeper into this asteroid. And so that is kind of why microwave telescopes are sort of on the up and up in this sort of field. In terms of how we differentiate between the surface and the inner sort of region of the asteroid, I believe we were able to somehow, I believe it had something to do with the facets and being able to um, see the change in temperature as the simulation would go on. So seeing the change in temperature, we knew that the sort of interface was able to penetrate the hypothetical asteroid and update those facets temperatures. If that is making sense at all. Does that make sense at all?
Yes, makes sense to me. Yes,
Okay, perfect, awesome. And did that answer your question or?
it did. It did.
Okay.
Thank you. Yes.
Okay, if you have any follow-ups, I can try and explain. But thank you for your question. Are there any
Awesome.
other questions? Perfect.
Nope.
Thank you guys so much for your time.
Awesome. Great job, Mariah, and thank you again for an amazing presentation.
Thank you.
All righty. So next up, let's see, I will share my screen for this one. Next up, we have Isaac Da Silva from Indiana University. They are an astronomy undergraduate and have always aspired to be an astronomer. Their main research area is in star clusters and also interest in exoplanets and machine learning. They work under Catherine Pawlowski, and their current research has been ongoing since May of 2023 and started from an astronomy RU called Alice Palmer Program. In the future, they plan on going to graduate school and pursuing a PhD in astronomy. And without further ado, Isaac Da Silva.
All right, hi everyone. Let me share my screen really quick. Alrighty, so today I'm going to be talking about the stellar parameters of red giants in the old open cluster NGC 7789. And what I'm doing is we're trying to figure out the lithium abundances in these red giants. And what we're trying to test this hypothesis that stars produce excess lithium when they transition from their red giant stage to their helium burning red clump stage. And what I did is I went through a variety of steps before I got to what I'm doing right now, because this research is still ongoing. But I'm going to go through each of these figures and I'm going to kind of explain what each of these diagrams are portraying. And so I'm going to start with figure one. I don't know if you guys can see my mouse. Can you?
Yes, we can see it.
Okay, awesome. All right. So the first figure is just a finding chart from Aladdin Light, and it just kind of shows a picture of the cluster. And if you notice, you can see some yellowish orangish stars, and these are the red giants that we're looking at. Now, figure two, I have a color magnitude diagram of some of these targeted stars. And this is after I de-reddened the color of these stars to account for interstellar reddening. And interstellar reddening can be quite a pain, as it can contaminate data and make things less accurate. And that's why I made it blue. My original color was red, but in figure three, I have a right ascension versus declination, and it's showing all of their positions. I like to think of right ascension versus declination as like their latitude and longitude in space, but I thought this was pretty cool. Figure four, uh-oh, what happened? Oh, okay. So figure four, I've got an HR diagram and it has their TEF versus their absolute magnitude. And if you notice here where I'm circling, there's like a giant little area of red giants. And someone might be asking, why is there so many right here? So what I learned is that some red giants, they evolve up to here, which is this little area is the same as figure two. They come up to here, but some of them, they can't sustain their size. So then they kind of drop back down into this little area. It's kind of sad. Like, it's just like, oh no, but yeah, there's like a whole bunch of red giants here, and they might sit there for I don't know how long, maybe millions of years. But I thought that was pretty interesting. Now, figure five, we have just synthetic spectra. This is like a prototype, and this is about to tie into what I'm currently doing. And this synthetic spectra is kind of showcasing different lines. You've got iron and calcium lines. And you see this area in the middle, there's these dotted lines, and these dotted lines are showing different levels of lithium, where the biggest dotted line has stronger levels. Now, how this ties into my current research is that we recently remotely used the WIN telescope, and this is located in Kitt Peak, Arizona. And what we did with that telescope is get the actual spectra of these red giants. And we're basically taking synthetic spectra and we're matching it with the actual spectra. And this will allow us to get the lithium abundances for these stars. So now in figure six, this is run through a program called Moog. And you have to do a lot of editing in the files. But you can see here, there's different colored lines where the yellow line, all the colored lines are synthetic spectra. The yellow line has lithium that's at a level 2 strong. You see a little red line there. There's lithium that's at a level 2 weak. And then this blue line is kind of just right. And then you'll notice also some white dots on here, and that's the actual spectra of the stars. And so what I do is I fit these little graphs together. And by doing that, I'm able to give a proper estimate of the lithium abundances in each of these red giants. And there's going to be a bit of uncertainty here and there, especially for this one. This one was definitely a bit harder to determine. But for the lithium levels that we get from these, we just refer to that as like the upper limit. So if we get like a number, say, for example, this one is less than 1.05, but greater than 0.55, we'll do like less than, and we'll put like a value. But it's really interesting. I have a total of 70 stars, and I'm about halfway done. I'm about like 45. And one more thing is that I also have like an Excel sheet that kind of keeps track of all the data that I input into this software, so I can keep track of everything. Have it right here if anyone's curious about seeing it. But yeah, and one more thing is someone might be asking why lithium? And the reason is, assuming that the Big Bang is true, there were two main elements, which were hydrogen and helium, but many people seem to forget that there was also a tiny bit of lithium involved as well. And because of this, I believe that lithium might be one of the many puzzle pieces involved into discovering the origins of this universe, which is pretty awesome. But yeah, that's it. If there's any questions, I'll be happy to answer them.
All right. Great presentation. There seems to be two questions from the audience. The first question says from Floor Brook Garden. Amazing presentation. I was curious, do you see a lot of variation in lithium abundances between the different red supergiants so far?
Yes, some of these stars that I've looked at are very weird. Like they should not have this much lithium in them. Usually stars use up, or I'll say lose. They use like most of their lithium, right? So that's already really weird. And um, for example, the one star that I had on there, let me pull this back up. This star right here, usually the average range for a red giant as far as lithium will be less than 0.55, but this one has more than that. And I also found that so far, as far as this research is going, uh, a lot of these stars have more than 0.55. So yeah, there's definitely a lot of variation. Some of them will have normal lithium levels, but I'm finding that more of them are having higher lithium levels than they should. I hope that answered your question.
Awesome. And there was one more question from Caprice Phillips. They ask, why did you choose this specific cluster? And are there any other clusters you are interested in?
So we chose this cluster specifically since it's an old open cluster. It'll have more stars that have aged and gone through their cycles. And since we're looking for red giants, this cluster has like a whole bunch of them. As you've seen, let me pull this back up one more time. As you see, like in figure 4, for example, there's just so many of them. And as far as any clusters that I'm interested in, well, if this research goes well and we do prove that the hypothesis is correct, that stars produce excess lithium, then this can lead me into other star clusters. Because just because we find that this cluster proves this hypothesis to be correct, it doesn't mean that it's going to be like that for a whole bunch of other star clusters. So yeah, in the future, if this goes well, I'll definitely try and look into more star clusters and see if the same thing applies before we can say that the hypothesis is generally true. So yeah,
Well, thank you. And thank you again for a great presentation.
thank you.
Okay, let's see. Screen, sorry. Tab. Try again. Sorry about this. There we go. Next up, we have Ana Carolina Buzelin dos Santos. They do research with thermoplastics, which began 2 years ago, and they've been working in the laboratory for 4 years. The objective is to acquire a solid propellant that will be good for storage, more economical, and more sustainable due to its ability to be reprocessed. The design of the constant volume pump and the proportions for the fuels were made in the laboratory. When they graduate, they intend to continue in the advanced propulsion area. Alrighty. Now we'll have a presentation from Anna.
Hello, can everybody hear me?
Yes.
I will try to share my screen now. Can you see the screen?
Yes, but there's oh, it's like loading. Yeah, we can see it.
Okay. Uh, Hi, I am Ana Carolina. I'm from Brazil. My work is in thermoplastic solid propellant, about the fabrication and the analysis of the data. The fabrication methods we use is pressing, casting, 3D printing or extruding, but due to the level of solids, since the process of in the mass of the propellant, there is 90% of solid when you press it, 82% when you extrude it. Is also a way you can 3D print it, uh, and 84% when you use the, sorry, 82 for casting and 84 for when you 3D printed or extrude. Uh, the difference between the percentage of solids is because higher is the higher it is, the more the specific impulse. So you get a better engine, better propellant using this. What we do, we take the raw material. You can see my mouse showing. You take the raw material, you grind it, measure, and we make analysis using NASA CEA, that is chemical is a software used for analysis of the number of chemicals you can use. We usually use the thermoplastics or TPU or plastisol, and we use the oxidizer, the uh, lithium perchlorate, and the boron or nanotube. Sorry, my English not the best. And also we use the and nitrogen perchlorate. Anyway, when we process, we take a tube of 1 centimeter wide and 2 centimeter high, and then we press it using a manual press. Then we go to ballistic test that we use a volume pump. On the top of the pump, we can have a sensor. We have a pressure sensor, a igniter, extensive exhausting valve, and a safety valve. The valve are used uh so we don't have too much pressure and don't explode everything. So is a safety measure, but you don't need because you go until 12 megapascal, and we to explode the valve the pump we need 64 force, so we are okay. Then we have the inspection. The inspection, we see the analysis of the data, using the ultrasound underneath that measure the length of the burning, so we can measure how fast it burns. If it is okay, we can use in a ramjet or a scramjet engine. If it's not okay, we go and reprocess and this and we for be a thermoplastic, we can cut it, grind it again, and we can reuse it. So it's okay to, and we have a longer life because of this. And since the way of uh, disposal is most used method of disposal is burning, we we since we can regrind and reprocess, we don't waste much material and don't go to the atmosphere. The long storage propellants, when they lose the properties, you can also cut it and use small amounts with the raw materials, so you can process it again and do it all over until you can have a good engine to a good propellant, solid propellant to use at the engine. And thank you. If you have some questions, I'm open to hear it.
Round of applause. Thank you. Thank you. I quickly see we have two questions. I saw Jasmine's hand first, so we'll start there.
Thank you so much for the presentation. It was absolutely amazing. I had a question. So, how can we identify and kind of synthesize thermoplastic polymers that exhibit the necessary thermal and chemical properties for use as solid propellants?
We currently we use the TPU and the sorry and the plastisol, which are resins. And these resins, they have uh, a good a chemical sorry, they have a good chemical property. And what we do, we put in the software that's called CEA, is from NASA. And at the software, you can see the data that shows that you have a good range of burning and go have a good specific impulse. And when we measure this, we can see which one is a better one to use. I don't know if I answer your question, but the
It did an amazing presentation again.
thank you.
Naya, see your hand raised.
Okay, yeah, an incredible presentation, Anna. I just wanted to ask, because I am a model rocket enthusiast, could you ever use these for model rocketry?
We the first one we used was candy propellant, which is one we do for testing because we needed something that to have more research about. So we use it to make data, and now we know how it works, so we can use our scare more experimenting. So yeah, you can use it in rockets that are smaller than the various of tons of material. You can use it also. Well, we expect to use it when we finish the research and chose the best one. We managed to take a fly and launch some of these.
Congratulations, that's exciting.
Thanks.
Michael?
Yes. So I had a quick question. Am I frozen? Oh, okay.
What?
Sorry, bad internet over here.
Okay.
I wanted to know, did you think about what might cause the differences in the solid particle mass between each method? And did you look into that when you did your research?
Actually, I didn't yet. I believe is because of the size of the grain. So you can put too much because we need to make kind of a moist powder to do the pressing. If you're gonna be put too much particle, you can press it. So you have to cast or use another method. That's why we have different solid mass.
Okay, thank you.
And we have one more question from the chat. Cherie Greer asks, are there limits to the long time storage and or reuse?
Yes, there is about 5 to 10 years that can be storage, or we lose too much of the properties, the mechanicals and the chemicals properties.
Awesome. Thank you again for an amazing presentation.
Thank you,
And
everyone.
mm, oh, uh, Anna, could you switch off your screen share, please? Awesome, thanks. Okay. Next up, we have Phoenix Avery's Sarian from The Ohio State University. Phoenix Avery currently does research in exoplanet atmospheres and spectral typing and characterization. In summer 2023, she started her project at the Lamont Institute, RU, at the University of California, Santa Cruz. Currently this summer, she is doing science education-based research at the Ohio State University under the astronomy department. In the future, she would like to potentially work in the areas of astronomy instrumentation and astroparticle physics. Ready?
Hello, can you hear me?
Yes, we can.
Okay, cool. I'm going to screen share. Okay. Can you see my screen?
Yep.
Okay, cool. So my project is on the reanalysis and recharacterization of Warner XS plus 3127B special typing. So just to give some background for this project, within our universe, we have objects known as exoplanets. And essentially, exoplanets are any planets that lie outside our solar system. And there is a certain kind of exoplanet known as brown dwarfs. And we get brown dwarfs when there's not enough hydrogen pushing out of a star to convert into helium when it is being formed. And so brown dwarfs are very unique. They serve as the bridge between low mass stars and high mass planets. It can hold complex makeups in their atmospheres and their weather, such as storms and cloud formations. And also we typically weigh brown dwarfs to be between 13 to 8 Jupiter masses. And so for a conversion, that would be 0.012 to 0.08 times the mass of the sun. And so in my project, I was looking at the brown dwarf, Warner XSB. And this brown dwarf was first discovered about 12 years ago, orbiting the host star, Warner XSA. And so right here would be an H-band image of Warner XSA, the star, Warner XSB, the brown dwarf. And so this system is estimated to have been found around 150 million years ago and is amongst directly imaged planets and high mass brown dwarfs. So in this image here, you can kind of see where the directly imaged brown dwarfs are in comparison to Warner XSB. And so within astronomy, we have a system called stellar classification in which we categorize certain objects by temperature, mass, luminosity, and composition. So in this context, 1R-XSA is an M2 star, while 1R-XSB was a previously classified L0 brown dwarf. But what makes 1R-XSB a special object to look at is its mass. It holds a mass of about 32 plus minus 6 Jupiter masses, which places the object in an intermediate regime in a more uncertain formation mechanism. And from this, we're unsure how this object may have formed, whether it was in the way of a giant cloud collapsing like stars do, or a core accretion where planets form in a disk of gas and dust around a young star. And so when the object was being first looked at over a decade ago, there wasn't a large library of different spectrum of other brown dwarfs to compare it to. And so for context in astronomy, we use spectrums for different objects that aren't visible to our eyes and are useful for knowing the chemical makeup of a brown dwarf. And we're working with different libraries now that's full of different brown dwarfs to compare 1R-XSB, such as SPECS Prism right here, and as well as SPECS SSD, which is from a low and medium resolution. And so we also have 1R-XSB spectrum data in the form of the SPECS Prism, SPECS SSD, and KEK-OSIRIS. And so KEK-OSIRIS is the highest resolution for all three of them. And so here in this graph, we have a visual representation of the different spectrum. And at certain wavelengths on this x-axis, there's large abundances of a specific chemical. So for example, there might be water, H2O at one point, there might be iron at another point as well, or methane. And so we perform something called a reduced chi-square statistic, which is a way to find a fair and average value to see how close a set of observed data matches closely to a model. And so the lower the reduced chi-squared value is, the more closely aligned it is to the model. So for example, for this L0, we have a 489 versus the M5, which is 2L1. And so this L0 would be more closely aligned to 1R-XSB's spectra. And we can also visually see this on the graph here too. At the bottom left, we have two graphs in which we compare 1R-XSB's data to both SPECS Prism library and XSD library. And all these different dots, individual dots, are brown dwarfs and spectrums of the brown dwarfs. And so on the x-axis, we have the spectral types listed below. And brown dwarfs are typically ranged from M, which is hotter in temperature, going through L, T, and Y, which is the coldest in its classification. And so on the y-axis, I performed the reduced chi-square statistic again. And the lower the points are on the graph, the more closely aligns to spectral typing to 1R-XSB. And so these three stars right here, they show the lowest chi-squared value for 1R-XSB, and that would be an L1. And then over here, we have it for the SPECS SSD. And with this library, it actually has partial spectral typing in its library, and the yielded result for this would be an L0.5 classification. And so when this object was first observed, it was said to be between about an M9 and an L2, but now with access to larger libraries, we can say that the best fitting type for 1R-XSB would be between an L0 and an L1. And so the importance of understanding intermediate mass brown dwarfs, we can find better clarity in the formation pathways, whether it's stellar formation or planetary formation, whether atmospheres are made of predicting their cooling and evolution of these objects, and the importance of objects within their distances as well. And so for future work, I plan to compare spectral classification using an index-based method, as well as atmospheric retrievals to explore its formation mechanism. And yeah, so that's pretty much it. I'm thankful for my advisors, Caprice Phillips and Isha Assadkar at Ohio State University. And I've been on this project for about a year, so very thankful. So thank you so much.
Great job. Let's go to questions. Mariah, I saw your hand up first.
Hi, this was an incredible and very interesting presentation. I just have more like a general question. I'm
Yes.
wondering if you are feeling inclined to continue work into the field of exoplanets. Like, do you think that this is going to be what you're going to specialize in, or are you hoping to branch out and explore other branches?
I would probably say that I enjoy exoplanets. I would like to stay in the field. Funny enough, I'm actually in the Netherlands right now for exoplanet 5. So I've just been here
Okay.
like the entire week listening to exoplanet talks, but I'm
Oh,
very,
nice.
very passionate about it. Being here at the conference has made me even more passionate about seeing in the field too. So, but yes, thank you.
Nice. Of course. Thank you.
All right. We have a question from Jasmine.
Amazing, amazing, amazing talk. So I had also a general question. How can we basically ensure like the highest quality and resolution for spectral data for the system? And what are some of the potential sources of noise and error that's in the data?
So for the different resolutions of spectra, I think from what my understanding is that it's important to use both low, medium, and high resolution. As like low resolution, they're quick and cover broad features. Medium resolution offers a balance in detail, and then high resolution is very precise as well. There has been some errors when I was going through the libraries. Like for example, I was maybe trying to look for like maybe like an M7 and trying to compare it to an XSB, and then it would just kind of like flatline against like the x-axis. So sometimes spectra isn't always reliable in a sense. That's why it's important to just have different resolutions and comparing it.
Awesome. Thank you so much.
No problem. Thank you.
And I believe that's all the questions. Amazing job again on the presentation. Oh, I think we got one last minute question from Michael.
Oh, okay.
I was trying to give everybody else a chance to go. But I just had, it's a quick question. How would you improve the results that you've gathered so far if you were to do this experiment again?
I think that would be like for the future work itself. So I I've picked down exactly where exactly like the spectra is. So between an L0 and L1 and going in like looking at the atmosphere, working with my advisor, I would do those next steps. I'm not sure that's very precise, but yes,
Okay, thank you.
no problem.
I have a quick question, if it's okay. So thank you, Rob. Please forgive me, as you know, I'm not the astrophysicist of Black In Astro, but I am curious. When you talk about comparing resolutions, are you doing that through some kind of like spectrometer grading, like varying the grading of your spectrometer? Is that something that you use in your methodology?
Yes. Yes.
Okay.
So the spectra is picked up from a spectrograph, and then there's different scientists who will upload the results of the spectra they collect from different brown dwarfs and different stars within that regime. So I'm able to use that data and pick out which ones would be specifically aligned to one of XSB's data.
Got it. Thank you.
No problem. Thank you.
Nice. All right. Next up, we have share my screen. Ready. Next up, we have Logan A. White from North Carolina State University. Logan is a senior studying physics at North Carolina State University with minors in computer programming and mathematics. She currently works with Carla Frolick on the simulation of Type 2P supernovae and utilizes a one-dimensional numeric framework to model the core collapse of stars and explores the effects of neutrino-driven explosions on simulated light curves. She has previously worked to characterize the redshift evolution of dark matter subhalos using in-body simulations with Versa Ushevik and Ethan Nadler, and to cross-calibrate magnetic solar measurements through machine learning with Vyacheslav and Sadikov, while she has done research within varying levels of astrophysical scale, from studying a single star to investigating galactic environments. She plans to apply to astrophysics PhD programs this fall to study the extreme physics of stellar and compact objects. Logan, you are up.
Alrighty. Hello, everyone. All right, the obligatory, can people see my screen?
Yep.
All right, wonderful. Okay, so this is work that I'm currently doing at my home institution, North Carolina State University, with Dr. Carla Froelich and her group. And we've previously heard about, stars in the middle of their lifetime, stars as they evolve, and what our study specifically looks at is stars at the end of their lifetime. So core collapse supernova mark the end of the stellar life cycle in the high mass regime. This means that we're looking at stars that are 8 times larger than our sun and up. And what happens is basically as a star grows older, it's burning through nuclear fusion, hydrogen to helium to lithium, and it goes all the way up the chain of elements until iron. And once it hits iron, it's no longer energetically favorable for the star to continue fusing. So what you can think of is its central engines, the thing that's keeping the star running and pushing outwards, cuts off. And then gravity takes over. So the star starts to fall in on itself, and this is where our study begins. So this is core collapse supernovae. And while we can't go and visit one of these supernovae, so we can't, visit and observe it ourselves, first of all, they're all very distant. And second of all, I'm not sure you'd want to be around when a star is exploding. We can observe the initial explosion and the energetic evolution of these events through something called light curves. So this is basically looking at how luminous or how bright one of these events are over the period of minutes to days. Specifically in this study, we look at type 2p supernovae. These are characterized by hydrogen-rich envelopes of these stars and a plateau phase light curve, which I'll explain a little bit more later. All of our work is simulation-based or computational, so the physics and observables of these events can be modeled in multidimensional simulations. 2 and 3D simulations are really great at modeling these events for specific cases. It allows for a detailed investigation of these environments or this physical evolution over shorter time scales. But what we want to do is look at a lot of different models. So we use 1D simulations. These utilize simplified methods. They produce observables for specific areas of study, which in our case is elemental abundances. And they let us do this over much longer time scales. So instead of minutes to seconds or seconds to minutes, we can go up to days or maybe even years. The specific model that we use to simulate these light curves we simulate the core collapse of these stellar models using the PUSH framework. So this is a one-dimensional neutrino-driven effective model. This simulates the initial collapse, so that fall inwards, the bounce or the shock wave outwards, and the early timescale physics of these explosions. So again, looking about the first 5 seconds of the death of the star. And we're exploding models that are 9 to 40 solar masses, so 9 to 40 times larger than our sun, from a 2016 set of progenitors. We then evolve these models to shock breakout, or to when the shock wave actually breaks through the surface of the star and the star explodes, in a sense, using a hydrodynamic radiation transport code known as SNEC, or the supernova explosion code. This produces bolometric and broadband light curves. So again, the observables that we would actually see here on Earth or using our satellites that we have in space. Okay, enough background, let's get to results. So moving on to these kind of central plots. This first plot up here is looking at explosion energies. On the x-axis, you have your mass of the star. On the y-axis, you have your energy. The right plot is looking at a 2019 paper that was also done in the group. This was exploding a set of models from 2002. The left plot is my work looking at the 2016 models. And the thing I want to point out here is that overall, we see that the trends of these explosion energies are the same. So this means that A, PUSH works consistently across different sets of models. And also you'll note that these crosses, which represent observations, agree fairly well with the explosion energies from both sets. This not only means that PUSH works across different sets of models, but it implies that PUSH also is using the correct physics, or is informing the physics of these explosions correctly and is matching up with observations. Moving on to some very early light curve results. This plot here in the middle on the right is looking at the pre-explosion radius versus the hydrogen envelope mass, so basically how compact a star is. And what our study focuses on is this upper right corner here. So these are all of the type 2p explosions. This star that you're looking at here actually corresponds to the light curves for this model. This is a 18 solar mass model, and this is the very first light curve that we've produced from our pipeline. We're very excited about it. The blue dashed line represents a previous work done in the group, again, using this framework, but on a 2002 model. And the purple line represents this current work. So again, same mass model, but the 2016 set. And the thing that I really want to point out here is that overall, most of the energetic trends in this light curve stay the same. So as we're looking at the luminosity of this evolving over time, we see this nice plateau phase, which is a characteristic of the hydrogen envelope of the star, but we note that there is some drop off as we get into later timescales. So this is an early indication that the composition difference between these stars actually does make a difference in the observables that we see. And then to further hone in on that last point, looking at these bottom two plots, again, on that x-axis, we have the mass of these stars. On the y-axis, we have a mass fraction, so looking at how much of an element is present in the star. This is right before explosion, so these are inputs to our model. And you'll note that between the 2002 progenitors, which you see on the right, and the 2016 progenitors, which you see on the left, we can already see that there's a lot of differences in the composition, especially as we get to higher mass regimes. This again produces some of those different behaviors and results that we see in these light curves. And we can also see that we would expect to see different light curve and different behaviors between different masses. So if we looked at an 18 mass star versus a 30 mass star, we see some significant differences, and this is what we want to further explore in these light curves. In terms of future, in my case, current work, we're computing light curves for all of the exploding 2016 models. This is to reproduce the statistical analysis done by Brendan Barker in 2022, where they also used the same set of models, exploded and looked at the light curves. They had a different initial framework, so they used something called STIR. We'll be using PUSH, and we want to see basically if there are differences in the effective models. And then finally, we're investigating the explodability and the nucleosynthesis or the abundance yields of all of these 2016 models with varying equations of state. This is to kind of provide greater diversity of these supernova simulations and also allow for more robust data science applications in the future. And with that, thank you, and I'll take questions.
Great job. We
Thank
have,
you.
yeah, no problem. We have one question from Flora Brogarden. Beautiful poster, Logan. This easily could be in an art museum. I agree. For the observations, how are the ZAMS masses derived? Are the pre-supernova are there pre-supernova images?
Ooh, first of all, thank you. Good question, though. I'm actually not sure. I know a lot of our observations were derived from previous papers, so I assume that those ZAM masses were inferred based on age estimates, looking at potentially, the star's positioning on an HR diagram pre-supernova. Most of these, I believe, are supernova that have occurred in the past 20 to 30 years. So I know there was previous history, a lot of these stars, but I can't speak to the exact method of derivation for the zero age main sequence mass.
Awesome. Thank you. Any other questions? Alrighty. Going once, going twice. Ooh. Thanks again, Logan. Great presentation.
Thank you.
Okay. All right. Next up, we have Kayla Smith from Central State University. Kayla Smith is a recent graduate at Central State, where she completed her undergraduate degree in environmental engineering. She is a rising graduate student at the University of Arizona in the Lunar and Planetary Laboratory. She is also studying the atmospheric chemistry of Venus, focusing on the formation and destruction of sulfur compounds. Her research interests lie at the intersection of planetary atmospheres and astrobiology. In her undergraduate career, she mainly focused on Mars's atmospheric chemistry, but moving into her graduate career, she hopes to expand the skills she has learned to exoplanet atmospheres. Ultimately, Kayla wants to utilize planetary atmospheres as a tool for finding biosignatures on planets beyond our solar system. And with that, Kayla, the floor is yours.
Hi, everyone. So thank you so much, Rob, for that introduction. I'm going to quickly take us to Mars for a little bit. So hope you like my background. Let me share my screen. Okay. Give me 1 second. Okay, is everyone able to see that? Awesome. Okay, so like Rob said, my name is Kayla Smith. I am a recent graduate of Central State University, and I am a rising graduate student at the University of Arizona LPL Laboratory. So I will be studying exoplanets in my graduate school career, but for undergrad, I have been studying Mars majority, and I'm also a research assistant at Caltech right now. So I've been at Caltech this is my 4th summer, 3 summers as undergrad, and then as I guess a little post-bac situation. So I'm going to present actually 2 projects that I've been able to do over my undergraduate career. I collectively entitled it The Photochemistry of the Martian Atmosphere from 2 chemical perspectives, but I kind of want to give a breakdown of each project. So the first one is analyzing the formation and deposition of H2SO4 in reduced environments, in this case, Mars. And the second one is the impact of novel water absorption cross-sections on present-day Mars. So I'll do the first one for sulfur. So how are these both correlated or related to one another? One, water is a resource that makes planetary bodies habitable, but that water proved to have escaped to space on Mars. And 2, sulfur isotopes can prove if a planetary body has been inhabited, even without the presence of liquid surface water. Again, sulfur isotopes kind of act as like a time capsule on the Martian geologic surface. And so we can understand if there's water once on the surface, and then sulfur isotopes can kind of tell us the age of those rocks. It can also tell us what the climate was like way back when. And so to answer all of these atmospheric chemistry questions, we use the 1D photochemical and transport model called kinetics, developed by, I think I said Caltech and JPL. It analyzes species vertically, so I can look at atmospheric escape to space, ground sinks, thermochemical reactions, and photolytic reactions, meaning if I have a water molecule, I hit it with a photon, it'll break apart into H and OH, and that'll kickstart an entire atmospheric chemistry cycle. It also takes into account eddy and molecular diffusion. And so going on to figure 2 here, I kind of wanted to just create a little bit of a cartoon to kind of say where this chemistry is coming from and how these chemical reactions are formed. And it's all kickstarted by the formation of SO2 and OCS. SO2 is known to have been kickstarted by volcanism into the atmosphere. And so we have suspected that Mars was once a very warm, wet, had a thick, dense atmosphere. At present, it's very cold, thin, and dry. So I love, love, love the evolution of the Martian atmosphere. I love how similar it is to our own Earth, but in a kind of a flip-flop kind of way. And so this chemistry really just puts into perspective for me what we're looking at and why we're looking at it and how H2SO4 is actually formed. And so moving down here, we look at the mixing ratios at 4 different atmospheric pressures. We have 7 millibar, 200 millibar, 500 millibar, and 1 bar. And so it goes from present day Mars all the way to early Mars with that 1 bar. And so we're primarily looking at the OCS and SO2, but we also vary the SO2 fluxes. OCS and H2SO4, but we vary the SO2 fluxes. And so we have 1E6, 1E7, and 1E8 assumed volcanic flux of SO2. We just wanted to see if we change the flux of SO2 by a factor of 1 between 1E6, 1E7, 1E8, what would that do to the behavior of OCS and H2SO4? And we found that in the pink here, we find that OCS peaks at about 200 millibar, but we find that H2SO4 actually decreases with increasing pressure. And so the number density relates to the surface pressure by this relationship. 1 bar of pressure has roughly 200 times more molecules than the 7 millibar case. As a result of this, the mixing ratio of SO2 will be 200 times smaller at that given pressure. And so that is just something that we wanted to see. We will obviously continue this work by adding an H2S into the model, kind of seeing how that will be added and affected in reduced atmospheres as well. And so here we look at deposition rates. Like I said, we can look at deposition and rainout. And we find a deposition rate of at least 2 times 10 to the 6 molecules per centimeter squared per second, which averaged over Mars's history, assuming no loss of surface sulfate, would translate to roughly, I think I got 22 to 25 weight percent. This is much higher than what MSL find, which was 2 to 12 weight percent. And so that reveals that there must be some unidentified loss mechanism. We suspect that it may be another sink for these molecules, but we are unsure, and that's something that we will figure out moving forward. And then and here's a little chart about to say like what the line means and like what flux we use for each molecule of SO2 and OCS. But we will also adapt this entire analysis to a warmer climate as well and try to see at at early Mars, how would this sulfur chemistry be altered as well. And so that is my first project that is still ongoing. Oh, sorry. And my second one is one that we are currently trying to write up and publish. It is the water cross sections project, which I refer to it as. It has been a project going for a couple years now, and we added in the water cross sections, extended water cross sections from Ranjan et al. 2020. And essentially, Ranjan found that this tail region here is non-negligible for water photolysis. Most 1D photochemical models, including kinetics, drop off at about 1950 angstroms, but this tail region here really showed us that water photolysis is actually happening at much longer wavelengths than previously suspected. And so to kind of go here, again, I made another cartoon to kind of show how this hydrogen chemistry is important and how it all connects together. Our kick started by H2O photolysing into H and OH, breaking apart, and that whole cycle will start to kickstart. And when there's more water around, there's more water photolysis able to happen because of the atmosphere of Mars, because it's so thin, and it's able to be broken apart. And there's more H and OH that are able to be photolysed and eventually diffuse up to space for the hydrogen. And so moving down here for the mixing ratios, essentially I took the cross sections from Ranjan, the extended cross sections, and I took that as a ratio I divided it by the older cross sections that dropped off at 1950 angstroms, and I took the ratio of the mixing ratios. And essentially we found this really big gap for CO and nitric acid. Again, mixing ratio on the x-axis, altitude on the y-axis, and again, we're seeing this really big jump from a really large decrease for CO and a really large increase for nitric acid. And we're wondering, why is that happening? Like, where's the CO going? Where's nitric acid going? What is being produced here? And so we found out that when we have more water photolysis going on, there's more OH that's able to be produced. And CO loves to react with OH, and that produces CO2, and there's a cycle that goes there. And so there's less CO building up in the atmosphere because it's constantly cycling because there's more OH around. On the flip side of that, nitric acid is actually being increased because NO2 loves to react with OH as well. And so when there's more OH around for the NO2 to react with, again, it'll cycle into that nitric acid, and the nitric acid will actually increase. And so looking right here at these color maps here, on the left is just kinetics by itself. We didn't add anything to it. We didn't do anything with it. We just had the 1D model itself. You can see that CO was really building up in that atmosphere. We wanted to understand why was that happening, again, because of that chemistry. So what we did was we added a latitude dependence from the 2D data provided by Graybus et al. 2019. We added in the water and ice data, so more water to the model, and we added in a latitude dependence. So it's ultimately a 2D model now. And essentially, again, with that CO being able to react with the OH, it has a very nice distribution around across the atmosphere at all altitudes and latitudes. And so again, that CO is not really blowing up anymore. It's still peaking right here, but it's not really blowing up anymore. It's more well distributed. And the last part of this project, I was really curious how dust storms can impact the chemistry as well. We all know dust storms are very popular on Mars, some even lasting for years. And so I really wanted to know how dust storms could impact the chemistry if we added in these extended water cross sections. And we found that utilizing the Chaffin et al. 2017 dust storm data, we interpolated that onto our altitude grid for kinetics. And we did find that hydrogen escape is actually it's actually increased with the dust storms with the added water that we had found from Ranjan et al. 2020. And so on the x-axis here is time in seconds. On the y-axis is the fractional change in mixing ratio. And each slice is an altitude going up. It's going down, but going up in altitude. And as you can see here, the mixing ratio at the bottom with this green line here of hydrogen is very, very, very high, meaning that hydrogen is able to reach the top of the atmosphere and eventually get pushed to the exobase and eventually escape to space. And so again, Water photolysis is really, really big. I think atmospheres can tell us so much about the evolution of a planet, and I'm super excited to apply this knowledge to exoplanets. And a moment for any questions. Thank you.
Great job. Let's see. So we have a question from Caprice Phillips. Great question. Great poster, by the way.
Thank
In
you.
in this field, are there any finds that different cross-section measurements may produce different results? Do these come from lab measurements?
Yes, they do come from lab measurements. Awesome question, Caprice. Yeah, they do come from lab measurements. And I think this is the most recent. For a long time, the Thomson et al. 1963 was like the bread and butter, like the basic of what we used. And that dropped off at about the 1950 angstroms. And so what Ranjan did was he applied this to actually abiotic anoxic exoplanets. So planets that had very little oxygen, but he applied it to exoplanets that had very little oxygen. But he used this model and he used lab measurements to kind of come to this conclusion that this tail region here is non-negligible. So, I mean, I don't know how much further we can go with the wavelengths as far as these cross sections will go, but I can almost guarantee that it will have a significant impact on chemistry, something as light as hydrogen that's able to be reacted with readily.
Awesome. I also had a question. Great presentation.
Thank you.
So I was wondering so I know you said you altered the flux of SO2.
Yes.
Have you thought of changing and this is more so relating to your goal or of getting into exoplanet as well. Have you thought of adjusting the abundances of ozone or oxygen in the atmosphere and
Of
how
Mars?
well of Mars or a potential like exoplanet template as well?
Yeah. I think there's a lot of exoplanet analogs that we have detected that have larger abundances of ozone and oxygen. That's an actually really good idea, actually. I don't know, I haven't really studied a direct exoplanet as of yet. I know that I will, but I also know that sulfur is such a good key component of what has happened in the atmosphere. So I think that maybe seeing how ozone and other oxygen species can interact with sulfur species, I think that can really tell us a lot about what's going on and how hot, warm the climate used to be, how habitable it used to be, how not habitable it used to be, and so forth. So that's an awesome suggestion. I'll definitely keep that in mind.
Awesome. And if we can definitely talk in the future because this has a lot of research. So
yeah, definitely. Yeah.
We have one more question from Ashley Walker. Have you looked at Venus's sulfur gas composition?
Yeah. So this summer, I'm actually working as a research assistant at Caltech. And we're actually adding sulfur to the Venetian atmosphere. But what we're doing is we're adding more complex sulfur species. And so I mean, Python hates me. So I'm currently in the works of trying to create a Python code that will allow me to compare the reaction rates of these sulfur species. So I'll get back to you on that, Ashley, but we're definitely in the works of doing that right now.
If you're interested in a code that may be able to do that for you, it's in the same suite as the kinetics model, but you could try using Vulkan or Helios as well.
Okay, perfect. Oh, wow. Thank you.
Yeah, no
Appreciate it.
Not a problem. Great job.
Thank you.
Any other questions? Going once, going twice. Awesome. Okay. Let's see. Share screen. Cool. Next up, we have Justin Ward from Sam Houston State University. They have worked on research, or they are a research assistant in the particle physics QCD lab led by William Shepard and Joel Walker at Sam Houston State University, where they ran collider simulations on the HPC. In fall 2022, they joined James Dent's lab at Sam Houston State University, investigating early universe gravitational waves and first order phase transitions, where they continue to implement code on the cluster. In summer 2022, they attended the University of Tulsa's SALT REU, conducting perovskite electrochemistry research with Gabriel LeBlanc. As a NAC alumnus, they worked with Ridi Bandiopadhyay at Princeton in summer 2023, probing Parker Solar Probe data for magnetic switchbacks, and they are currently collaborating with Ridi again. Their career goal is to work in multi-messenger astronomy as an observer and analyst. All right. Justin Ward, you have the floor.
Hi, everybody. Um, I think I closed my poster. All right. Sorry about that. Here we go. All right, I'm gonna leave the Zooming to y'all. I also want to say Happy Freedom Day, everybody. So I'm Justin. I'm a senior at Sam Houston. I work with Brittany on this project. We're doing a data analysis of Parker Solar Probe data. So Parker was launched in 2018, and it's an 8-year mission. Essentially, they call it to touch the surface of the sun. It's taking ever shorter orbits between the sun and Venus, and it's using Venus for gravitational braking assist, which you can kind of see in this panel here. One of the features that Parker has found in the solar wind are what's known as magnetic switchbacks. And these switchbacks were first noticed with the earliest probes that we sent up back in the 60s. But they haven't really been characterized or understood until this modern project. So what happens in these regions are the radial component of the sun's magnetic flux turns back sunward for some time before moving back anti-sunward. And these disturbances, it's essentially like a S shape like this. It moves out throughout the solar wind. And the formation mechanism for this is the foot point of one of the field lines being at a coronal hole, this distributing slower solar wind. As the sun rotates, that foot point moves to a hole that's ejecting faster solar wind. So it grabs the field line and drags it along ahead of itself. One of the things that, well, I guess not one of the things, you'll hear me keep referencing radial, tangential, and normal, and that is the coordinate system that we use to evaluate these things. There's a spacecraft frame, that's just a convenient frame for analysis. But one of the questions that's arisen during the investigation of these switchbacks is, what do we expect to happen in the tangential wind, in the solar wind in these switchback regions? Previous works already showed that the radial component of the solar wind increases in the switchbacks, but nothing's really been done to investigate the tangential component. So that's where we stepped in. Here you see I justified that using Lorentz force. Honestly, if you go into the literature, most of the literature is, if you just look at the early analyses, that's enough to motivate a further investigation. So the first step was to reproduce plots from a paper by Nick Swadron and Dave McComas, who are the head of the space physics lab at Princeton. And I'm not going to belabor all the plots, but I will draw attention to 2 specific ones. Here we have magnetic flux. Each different color represents a different component of the magnetic flux. And then this one is going to be, or it's not this one, it's this one here. It's going to be the tangential component of the solar wind. So highlighted on this plot in green are the switchback regions, and those can be contrasted with the rarefaction region, where there are also fluctuations, but they're much slower, much more gradual. So you can see the fluctuations in the tangential velocity are a lot more gentle, and the jumps or dips in the radial component of the magnetic field are much smaller and much shorter in duration. So the purpose of that was to say, yes, I understand the data. Yes, we have the correct data. And yes, we're looking and analyzing it, right? I was able to do that. So then the next step is to try to automate that. So we looked again to the literature. This is from another paper by Pecora et al. And this is using my code to try to match the switchback that they found. And what you can see here is that I had generally the same shape. I lose amplitude a little early. So my first code was not 100% as far as selecting switchbacks, which meant that I had to turn to manual definition of the switchback region so that we could take some statistics. So jumping on to, I guess, the money plots, I have histograms for switchback regions and rarefaction regions. And the switchback regions show a slight left skew, which is indicating a preference for higher velocities. The rarefaction region shows an obvious right skew. The majority of the velocity readings were in the lower bins. And that's really evident when you get, if you look at the actual counts. I actually had in the top 3 bins, even though there was far fewer data points in the switchback regions, I had much higher counts or significantly higher counts in the higher velocity bins. So that's showing a preference for higher speeds in the tangential velocity in switchback regions. Now, to be clear and to be fair, this analysis was only over a 10-hour period, so we can't make any conclusive statements. Also, my code still needed some help by the time that this analysis was put out. So the obvious next step is to fix the code and analyze larger data sets and take some real statistics. And that's the direction that we're on now. Currently, I'm still working on the code. I'm adding functionality and accuracy. This is a reproduction using the current code of that same 10-hour period. And you can see that it's gotten better at selecting all the regions. And it's also, we can set it to arbitrary parameters. So we can essentially test anybody else's data sets. Right now, I'm running through all the close encounters so far, or all the close encounters that have data releases, and I'm actually trying to get my statistics run right now. Thank you for your attention. Have a good one.
Great poster, Justin. Any questions?
I had a question. Sorry, just looking for that mute button. In terms of adding extra layers of functionality to your code, what extra layers were you thinking about adding in particular?
So to start, like the original code was set to say, okay, we're in a switchback when like this parameter Z is based off of this deflection angle BR from a 6-hour average of the total. So my original code was like anytime Z is over 0.5, then call it a switchback and track that. Now I have it like I'm setting it up. So number one, we have to be looser with that parameter. Looking at the literature, that's not really accurate. And like I said, nobody's really investigated it, so it's still kind of murky of like what actually constitutes a switchback, and we're still working on that. So I'm set up to be a little more flexible there. I'm set up to basically to set my time intervals better. Anybody like you can essentially enter a time interval, say, hey, I want this area, I want to evaluate this time interval, and it'll go through, find all possible switchbacks. And then what you do instead of ending up with a bunch of things that you have to filter out later, it goes individually one by one, and then either you approve or reject that specific region on the plot as a switchback. So then it should return, like you should be able to return statistics for any time interval. And I'm gonna keep working with it as like, you know, as we figure out things to make our discernment better, I'll try to include those in the code.
Okay, yeah, that is I would I would say that that's a really good, you know, forward progression, especially if it's a parameter that's not well defined. Thank you.
Cool.
We have another question from Megan Bedell.
Okay.
A great presentation, Justin. Does switchback behavior depend on where in the 11-year solar activity cycle you're looking? Are your data from low or high activity times?
My analysis hasn't gone far enough to make that kind of claim. And as far as I'm looking at all times. I'm looking at all times. Specifically, I'm looking at close approaches, which they count wherever the spacecraft's within 0.25 AU. So those generally end up being about 11-day periods. And right now I have the data from 2018. It launched in October 2018. So I have the data from 2018 through like September 2023. I think it's been back around at least one more time since then. That data is not out yet. I'll let you know, or look for a paper whenever we get these statistics done.
Cool. Thanks again and great job, Justin.
Yeah. Thank you.
All right. Next we have loading. Right. Brianna Sampson from University of West Indies. Last year, Brianna had the opportunity to research double radio sources associated with active galactic nuclei to discover giant radio galaxies in the TIFR GMRT Sky Survey. Using a proof of concept method, it was discovered that there were potentially 1,197 previously undiscovered GRGs in the TGSS data. This was their first time conducting research, sorting data, and analyzing the quantity of the results. Since this was a proof of concept method, however, they are currently working on the project again to deduce more conclusive results. Even though their main physics interest is theoretical and particle physics, they particularly enjoy astrophysics with its eccentricities such as dark matter, exoplanets, FRBs, and of course, galaxies and active galactic nuclei. Without further ado, Brianna.
Hello, can everyone hear me?
Yes.
Okay, great. I just have one question. Do I have to use the poster that I sent you, or can I use another poster that I did this year? The poster that I sent you was a very old poster, and because I got the information about the BIA very late, I didn't have time to make a new one.
I believe that should be fine. So you're able to share the screen, so you have preference to that extent.
Okay, great. Thank you so much.
No problem.
Can everyone see my screen?
Yes.
Okay, so. Hello, everyone. My name is Brianna Sampson. I am a second-year physics student at the University of the West Indies in Trinidad and Tobago. Last year, I had the opportunity of working on staging for giant radio galaxies in the TGSS survey with my advisor, Dr. Jan Gordon from the University of Wisconsin-Madison, as well as two colleagues, Soren Ramdani and Eric Hooper. Giant radio galaxies are double radio sources associated with active galactic nuclei or dragons that have grown to megaparsec scales. They are rare and their angular size in the sky makes it difficult to detect through automated routines. These dragons may affect formation of new stars in its galaxy and in its local environment because they may be a part of the regulation of material into and out of these galaxies. A dragon can become a GRG in a less dense environment as the destabilization of the AGN jet is prevented. To search for these GRGs, I had to use the Dragon Hunter algorithm developed by Gordon et al. In 2023. And I use it to find double lobe sources in the TIFR GMRT Sky Survey or the TGSS data. For those sources with a host ID and a redshift, I applied a largest linear size or LLS greater than 0.7 megaparsecs, and 17,724 sources were reduced to 1,441 candidates that could contain GRGs. I then had to create 1,441 radio optical images using Python, where the radio image of the dragon is represented as Fox contours on the optical image. I then compared 30 images from the TGSS survey with the corresponding image from the faint survey, the first survey, which is faint images of the radio sky at 20 centimeters. And I did this on 30 images using DS9 software. Upon visual inspection, it was found that 143 were spurious and removed from sample. As you can see here, these are the characteristic lobe shape of the dragons. And these dragons are formed when supermassive black holes accrete matter and launch highly energetic particle jets of glowing gas out at its poles. And these jets can travel large distances before becoming these massive radio-emitting lobes. And you can see the characteristic shape of these lobes here in all three images. But in the spurious images, however, they don't have the two lobes. And in many other images, you can see that the images were of two different lobes of two different dragons, or a zoomed in image of one lobe. After the comparison with FACE, and I did this comparison because FACE has better resolution, but covers less of the sky, so it was used to calibrate the data. From the comparison, 27 out of 30 were confirmed to be dragons. And this proved a 90% reliability within the data. And in this picture here, you can see the comparison with the FACE and TGSS images. FACE is on the left and TGSS is on the right. Afterwards, I then cross-matched my list of GRGs with the known list of GRGs, and I found that there were 101 matches within 90 arc seconds. And over here, you can see the first peak, which is the 101 matches of known GRGs. And then this second peak here is the previously undiscovered GRGs in the TGSS data. In conclusion, it is expected that there are approximately 1,000 previously undiscovered GRGs in the TGSS data. But this is a proof of concept method, so this year I will be working on providing a more conclusive list. And this list could be useful for testing AGN feedback, which is the impact of the local galaxy environment on those jets, and vice versa, as well as testing AGN jet propagation and production. And this list could also be useful for testing radio galaxy evolution because of the large sizes of the GRG. that is the end of my presentation. Thank you for your attention. Are there any questions?
Great job, and thank you for your presentation. I'll open the floor to any questions. All right, we have a question from John Hood. Would it be safe to assume that the Spirus GRGs are blazars and not quasars?
It would not be safe to assume that because this Gordon et al., the Dragon Hunter algorithm that I said that was used was developed for the VLAS survey. That is the Very Large Array Sky Survey. And VLAS, FACE, and TGSS have different resolutions and frequencies that they operate at. So the Dragon Hunter algorithm was not made for the TGSS survey. So because I used it, some of the mistakes are reflected in the spurious images. This one here has no characteristic lobe shape. And this second one here is basically the zoomed in image of two different lobes of two different dragons. And then this third image here is just a zoomed in image of one dragon. So this say I'll have to work with my advisor on creating a Dragon Hunter algorithm with the specifics of the TGSS data in mind. Are there any other questions?
Yes, I believe we have one from Michael.
Yes, it's not so much a technical question, but more so asking what program you're using for your poster display right now, because it's very well put together. So I'm just curious.
Oh, this was my poster from AAS. That is the American Astronomical Society. It was from the 243rd meeting in January for the winter meeting.
Okay, and are you using like a website or what?
Yeah, it's the AAS website for the 243rd meeting.
Okay, all right, thank you.
No problem. Are there any other questions?
I think that's all the questions that we have. Great job, Brianna. And
Thank you very much.
yeah, no problem. And great job, everyone, to those who presented today. That concludes all the presentations that we had scheduled for our showcase today. I'll also like to give a special thanks to all of our judges as well for their time, and as well as thank you to those of Whitman Barber for the ASL translation. And yeah, thank you again all for being here. And that concludes our event. Thanks, everyone.
Great job, everyone. You guys are brilliant.